Today, we are looking at reaction kinetics. And this is really where we start looking at potential energy diagrams. Energy is hugely important when it comes to chemistry because energy is involved in breaking and making bonds. And sometimes we like to get energy from reactions or have it absorb it. When atoms approach each other to make bonds, they're moving rapidly. That means they have lots of kinetic energy. But as they start interacting with other atoms, they're going to slow down. And that kinetic energy is going to change to potential energy. And it turns out this kind of information, these changes in energy, can be shown on a potential energy graph. Now, what we're seeing here is two atoms approaching each other and what happens to their energy at different distances. In this case, they're far apart, not much impact. They're closer together, but there's not much change in energy. Right here, we have a nice overlap. Believe it or not, that's two atoms. They've got some sort of bond in the middle. And this is saying this is the optimum length. This would be the bond length, the distance between two nuclei. If we have two atoms and they're like this, there's too much overlap. And we're going to have the positive nucleus of one repelling the positive nucleus of the other, and we got a lot of electron overlap here. That becomes unstable and the energy goes shooting up. So that's a diagram in your textbook that I've just chopped into this part here. So we want to look at energy and bond breaking and bond making. So you should remember things from grade 8 and grade 10 and grade 11. In grade 8, you're taught about the kinetic molecular theory. And if you think about melting a solid, when you add heat, what you're doing is you're causing particles to jiggle around. You're causing them to have enough motion that the particles break apart from each other. When we have bond breaking, we know that's an endothermic process, and kinetic energy is converted to PE. So if we add energy, if you're making a chemical ice pack or using a chemical ice pack, or if you are boiling water, that's an example essentially of bond breaking. On the other hand, bond forming tends to release energy, and potential is converted to kinetic, and that kinetic energy goes outwards from the source. And so here we're looking at an exothermic process. PE diagrams give us a lot of information about reactions and ultimately reaction rates. We should remember about exothermic and endothermic. But we're also going to learn about something called activation energy. Activation energy is the same as energy of activation. It means the exact same thing. From these PE diagrams, we can get a clue about whether a reaction is going to be fast or slow. And it'll be fairly straightforward to interpret. So we're going to look at some simple diagrams here. So what have we got going on? Well, 1 represents the energy the reactants have. 4 represents the energy the products have. 3 represents the change in enthalpy, the difference in energy between products and reactants. Boom minus boom. In this case, delta H is positive, so we can see this is an endothermic process. Now you're wondering about this peak. Well, this peak is something called the activated complex. This is the energy the activated complex would have, all the way from here to here. But number 2 represents the activation energy. That's the energy the reactants A have to have in order to form the activated complex, in order to have the chance to make the products. If you don't end up with this amount of energy to make the activated complex, if you can't make that, you can't make the products. So we can see in this case the forward reaction has a bigger activation energy than the reverse. The reverse reaction has a smaller activation energy. And that is shown here. This is an example there. It says endothermic, as we're making something like acetylene. So 1, the energy of reactants. 2, activation energy. 3 is delta H that you should remember, the heat of reaction. And 4 is the energy of the products. So let's look at another graph here. And if the last one was endo, you can kind of guess this one's going to be exothermic. So in this case, that crazy thing coming down, this turns out to be fast and exothermic. It's fast because it doesn't have a very big activation energy. That's a small hurdle to clear. And it's exothermic because if we look at our reactants, they have more energy in the products. So this gap in energy, the delta H, is what can be released and used. So fast because of small activation energy. Now we're looking at endothermic again. Slow and endothermic. In this case, we have a large activation energy going from here all the way there. So not many particles are likely to have enough energy to clear the hurdle, certainly at room temperature. We'd have to apply heat or something to make that happen. So that's it for that PowerPoint and a bit of an introduction to PE diagrams.